will not entertain the question during the test, right? You know me. You know me so well. Okay, so in the previous class we have know what is speed of sound, not sound of speed. Usually I tend to interchange it. Speed of sound and Mach number, and analyze the effect of Mach number on the fluid flow. You know that why we use Mach number, even though for the same velocity it may give you a different Mach number, right? Different temperature, you got different Mach number, which is inconsistent. It's supposed to be the same, but anyway, it's not. And we're still using it because it determines whether your flow is sonic, subsonic, hypersonic, and transonic. Okay, and then we know how to analyze a one-dimensional isentropic flow when there is no work coming in and no heat transfer. And this is what we have learned last week in the last lecture. You can calculate the C. For the ideal gas, it is KRT. For non-ideal gas, it will be dP over d rho. It's given there at a constant entropy or at constant temperature, right? And then the variation of pressure within flow area is given here. So you know that for a subsonic flow, if you want to increase the velocity, you need to make it smaller. But for a supersonic flow, if you want to increase the velocity, you have to make it bigger, right? That's the importance of Mach number. For a sonic flow, you can see that the change in the area will not give a change in the velocity. So doesn't matter what, at Mach number 1, if you change the area, mass flow rate will remain the same. Okay, will remain the same. And this is some of the relations that you get. Okay, you don't need to remember this one. Why? Because this thing is only when Mach number is equal to 1. So you can get this by setting this into 1. So this one, if it is there in your exam, it will be given, but this one no, because it's the same, right? So you don't have to worry about the Mach number. Whenever you have Mach number 1, you got it. Okay, so now, okay, we want to see how the isentropic flow, how the properties change for an isentropic flow within a nozzle. Okay, I told you this one is the Saturn engine. This is the one that drives human into the moon, right? In one Apollo vehicle, you have 5 of it. Okay, and it can blast you into 11 kilometers per second, so that you can escape the gravity of the Earth. Right? Now, you want to see what is the effect of back pressure applied at the nozzle. Okay, we start with the converging nozzle. Okay. Okay. In reality, how do you do this is by connecting two big tank. Connecting two big tank like this. Okay. So your nozzle is over here. You have a compressed tank over there and compressed tank over there. Okay. This is how you do it. Actually, it's not simple like that. It's like this. And then you have a valve here, valve, connected with a vacuum pump. Okay, so this is how it looks like. Now, the first case is when the pressure over here is equal to pressure over there. What will happen? There will be no flow. Right? No flow, because the pressure is same. So you can see when the PB is equal to P naught, PB is the pressure over here, the back pressure. Right? The back pressure. And P naught in this case is equal to P1. Why? Why? Because the velocity over here is close to zero, right? The tank is in stationary condition. When we are talking about the inlet condition, because this is a big tank, pressurized, very big tank, it's not small tank. So basically the velocity here is more or less zero when we are dealing with this. So your P1 is basically equal to P0. Okay, so when your P0 is equal to PB, of course there is no flow. Right? It's similar with you have a glass of water, you put a straw there, you don't do anything, no flow. You got no flow. But when you put in your mouth, you provide the suction, then you get the water flowing through your throat. Right? So the same goes for this one. If you do not have a pressure difference, there is no flow. Okay? Now I open the valve. I open the valve. Right? Then the pressure here will start to drop. Okay, get the concept, eh? Now I close it, I open it and I make it goes down into 0.2. Okay, this pressure now is less than P0 but still higher than P star. Remember what is P star? Critical pressure when the throat is having Mach number equal to 1. So when your PB is less than P0 but still higher than P star, this is what it looks like. So the pressure is going down from the inlet into the outlet. Okay, so this is the condition. Now, if you reduce it further, you open it again until this PB equal to P star. When the PB equal to P star, you know that your throat now is at a critical condition and you get a sonic speed. Okay? Now, what happens if you open it further? You open it, you release, not only you release, you suck it. So you provide a suction to this tank. So now this tank, the gauge will be negative gauge pressure. The absolute pressure is still positive because absolute pressure never negative. But the gauge pressure is negative, vacuum. Okay, total vacuum means your pressure is equal to 0. Okay, that is where you cannot live. Because you don't have air and your blood will go out from your body, right? If you are living in zero pressure magnetic, absolute. So you do that, what will happen is the PB will be decreasing, right? But the pressure in here will remain the same, P star. Okay, so now, let's see what we can do with the mass flow rate. You know that the mass flow rate is rho times A times phi. Okay? And rho is PRT for ideal gas. And velocity is Mach number to the square root of KRT for ideal gas. We are talking about ideal gas. This one is only for ideal gas. So you got it equal to Papa, Mama, KRT, right? Pressure, area, Mach number, specific heat ratio, gas constant, and temperature. If you expand it, you will get this one, right? Because your pressure is keep changing, you do not want to use it, you want to use pressure stagnation, right? Similarly, the temperature keep changing, right? Across the pressure here is different with the pressure there, is different with the pressure there. The temperature is the same. Changing also. So you do not want to use that. So you want to use P0, 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 T0, 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 because then it will be constant along the nozzle. So you change it into P0 and T0. So this is the correlation if you want to calculate the mass flow rate inside the nozzle. Okay. Now, what happens if your Mach number is reaching 1, or when your throat is at the critical condition, when the back pressure is equal or less than P star or pre-critical, then your Mach number will be 1. You plug in 1 into there, you will get this. So this one is the maximum mass flow rate you can get for any nozzle. Okay, this is the maximum. Any question until that? But don't worry about this equation, you just need to get this. Because from there you can calculate rho is P at that condition, right? If I ask you to calculate at the throat, it will be PT R T at the throat. You can calculate that. Velocity is Mach number at the throat, K, R, and T at the throat. So you don't need to remember these two. Okay? You can remember the name of your boyfriend, the name of your boyfriend father. Still you can have spacing for that. So don't worry to remember this. You remember this one only. Right? You know how to get it.